The topic I'm going to talk about today is predictive maintenance for transport system, and I'm focusing, of course, as well on the fact of how can this improve the sustainability performance for a company as a whole. So, maybe all of you, or at least some of you, do know this situation. You make an appointment at an auto shop, somewhat 3 weeks upcoming, and then you go to the auto shop and, well, if it's the same for you as in my case, you come out with a pretty light pocket. The things which are bugging me about this situation all the time is that you're investing a lot of time, you're investing a lot of money on it, and the third thing maybe is money which isn't really needed to be invested in, because this thing is preventive maintenance. So maintenance which is done just to make sure that everything's right, even if everything is all right already. Therefore, this should be the motivation for a more smart way to do maintenance. Well, in order to introduce you to the topic of predictive maintenance, we should clarify the 3 levels of maintenance which are known in research. The first one is corrective maintenance, or as we also call it, break-fix maintenance. So if something breaks in your system, be it a transport system or an industrial plant or something else, you fix it. The second level will be preventive maintenance, which is the very thing we just saw on the first slide. So you do something in order to prevent that an outage, a breakdown could happen. And the third level, the thing we are researching on currently, is the so-called predictive maintenance. Means we're predicting outages, and therefore we're trying to make maintenance smart, and especially the scheduling of maintenance. So the way we do that is we use condition monitoring via sensors and data analysis based on this based on the collected data by these sensors. As my predecessor just told us about, this is one thing which is currently ongoing, that transport systems or production plants or whatsoever are more and more equipped with sensors in order to measure their behavior. So, as I just said, the current application areas are production plants, which is, of course, tightly connected with the driving force in this development, Industry 4.0. For example, there are implementations in semiconductors and injection molds, and regarding transport system we have void detection underneath railway tracks. We have the concept of replacing car cam bolts, not when they actually break, but when it's most likely that they break in the very next time. As well as what I'm going to present today, the performance of engines, especially for critical engines in aircraft, meaning turbofans. Okay, when we are talking about predictive maintenance, we also should think about the variants of detections we have in there. The first step is to analyze if a system is working correctly or not, meaning we have to detect if there is some anomaly ongoing, or if the state is currently okay and the whole condition of the system is well. The second thing would be the second level, a little bit more difficult in most cases, is the breakdown prediction. So we really produce a value, a so-called remaining useful lifetime, which means I can predict that, for example, a transport system is only behaving well just 3 more life cycles more. And the third level would be a quality loss prediction, which is mostly interesting in industry when I'm producing products and I want to predict the amount of outage or the amount of erroneous products I will produce in the very next period. The effects of such a smart way of scheduling maintenance is, of course, I can shorten the downtimes of some machines, of transport systems, and therefore I can increase productivity and also profit. Yeah, I can also anticipate the potential of failure, and therefore I can mitigate the risk of workers on the one hand, of passengers in transport systems on the other. And for sure, I also can avoid replacements because I do not do it in a preventive way. So I just, replace a cam belt every 5 years or whatever. I do it just if the cam belt has a factual defect. And this is something which, of course, again, mitigates costs regarding time, material, energy, but is also the driving power for the improvement of sustainability and the sustainability performance of a whole company. So this is the link to the name of this whole conference. Well, we had a lot of terms now, and there are some more upcoming, which are tightly connected to the topic of predictive maintenance. As I earlier mentioned, the driving power behind predictive maintenance is Industry 4.0, or smart production, or the digitalization of industry, which is a very hot topic right now. Also linked with Industry 4.0 and predictive maintenance, of course, are the terms cyber-physical systems, Internet of Things, cloud computing, and so on and so on. And you might better understand how this is all linked by looking at this graphic, which some kind of illustrates how a prototypical predictive maintenance setup could look like. We have our transport system here, our respecting a production plants, equipped with some sensors, each presenting an individual and therefore refer to the Internet of Things, sending data continuously to some cloud process, which links to cloud computing, getting pre-processed there, getting forwarded to so-called analysis components, which are in our case prediction models, getting further forwarded to a decision support system, which is actually afterwards triggering maintenance actions, which are sent, for example, to some maintenance operators, so real human beings working at the edge, having some head-mounted displays, for example, on their head, or having some tablets in their hands, and then operating according to the decisions which have been made by our pipeline or life cycle, as we call it. Maybe one step back. The thing we are focusing in this, or I'm focusing in this presentation from this point down, is the development of prognosis models and the prediction of the remaining life cycle of the transport system. And the thing we tackled is a Turbofan degradation benchmark data set, which has been produced by a group of NASA, and using a simulation in MATLAB Simulink. Maybe some of you have already experienced that, being at the airport and sitting at the airplane looking at some maintenance operators, and as you can see, there are quite some people required. As you can imagine, this is a very costly process, and this is something we could also do in a more sophisticated way, do in a more smart way. Not doing it, maybe doing it after, do a quick check after every flight, but not having to do an intense check just because to be preventive. In contrast, we could do it in a more prognostic way, using the data we are already actually collecting when we are thinking about turbofans such as these. Okay, the data they produced look like this. These are common data sets, having some operational settings on the left-hand side, having up to 21 sensors on the right hand, and what they have given out to the competition participants of this benchmark assessment was exactly one number. This is the so-called run-to-failure situation. So they simulated the destruction of turbofans. This is a pretty hard, pretty difficult benchmark data set because you do not know if and how you can use all the data there if you just have a straight zero down there. They handed out one training data set and one test data set, And in a test data set, it's even more hard because you do not know that there is a straight zero there. Of course, you have to do something for your reward. You have to predict the number of remaining life cycles at the end of the data set. And if you can think of predictive maintenance, how it could be researched, and this is a very, very close to reality example. Because if you want to develop this kind of smart maintenance, then you probably choose the way to go to your product and try to destroy it and collect data until it is destroyed. So if you have collected this data, then you try to find something out of it. But the thing is, in this data set, you do not know when the destruction started. This is one major challenge. In this case, we have 22 life cycles left. Okay, we have 100 units of these turbofans available, all having 150 up to 250 rows per unit, and then having, as I said before, some sensor values and operational settings. Well, and the major difficulties are that the damage propagation starts at some point, we do not know when, which is also in reality the case. We do not know when the actual damage happens in most cases. We just know the effect that the machine or the transport system is dead. And therefore, I'd like to emphasize the importance of not just using thresholds, not just thresholds, but to use prediction models. As you can imagine, a threshold is something like this. We have some sensor, and if there is some peaks or a current or a certain trend, and this exceeds the threshold, then I can somehow figure out then that something is not going on right. In this case, we would have here a maintenance case. But as I said before, this is something we would call break-fix maintenance. We have the effect very visual here. Something different is shown in the second figure. As you can see here, the behavior of the sensor just evolves and develops. And the same thing goes for this, when certainly sensor values start from running alongside and then currently start to diverge. And the same, or the even harder thing, is when the damage propagation starts at a hidden point. So this line, this gray line, is actually hidden, and you do not even know when it starts because your sensor values do not cover the monitoring of the damage. Okay, what we employed to tackle this problem is we try to develop prediction models. This is done by so-called machine learning, a data analysis approach. We use the method of symbolic regression, which means we're trying to find out of these data sets a function, an estimation for the remaining useful life cycles. Therefore, we employ several symbols, since a symbolic regression function, such an estimation function, is a mathematical function. We employ several symbols and try to find the best function, which gives us a reasonable estimation of the remaining cycles. This is driven by GP, so-called genetic programming, which is an algorithm inspired by nature and by the natural evolution of individuals. Therefore, we try to develop these individuals, shown in the right here, and try to find something like this down here, which is more or less close to optimal after the algorithm has run for a certain amount of generations. These models look also like these syntax trees, and since we're stating that we're using ensemble models, we're employing more than one model. We develop an ensemble of models in order to represent all the potential error states. Therefore, we used our open source optimization environment heuristic lab, which is basically applied in three areas: in database analysis, in production planning and logistics optimization, and as well as in simulation-based optimization. It offers a large set of algorithms as a rich GUI. It is possible to distribute the computation of it, and it is the base of a lot of research projects. Okay. Well, in there I have the modeling process, but since I'm running out of time here, I guess I will just step it over a bit, or is it already shown? Yes, okay. What you can see here, we are loading the problem, which is the symbolic regression problem, which is used to import this comma-separated file, meaning our benchmark data sets, and then we're starting the algorithm and developing our different syntax trees, meaning our models, in order to predict our remaining useful life cycles. Okay, well, let's move on to our results we achieved in our benchmarking competition. As I just said, we used a genetic programming algorithm driven by a so-called offspring selection genetic algorithm, and we employed several of these models in order to do our estimations. Therefore, we gained a prediction quality of 21, more or less 21 absolute error, which is very, let's say, not that impressive. It's okay. But if you think of that, these values range from 150 up to 250 remaining life cycles, then 21 on average on an absolute error is not very impressive. Therefore, we tried to do it in a different way. We used random forests, another algorithm applicable to machine learning, and we achieved almost the same results. So what we found out when we investigated our data set a little bit more intensively, that our models are too cautious. Meaning, as you can see here, we would send in the Turbofan too early, which is not a bad thing, actually, if you can think of the real world situation, but it would be nice to have something more precise. And therefore, we did it the other way around and tried to implement the first level of maintenance detection. And this has been done by real-time state detection. So we trained a normal behaving state with our prediction models, then we trained an erroneous state, and then we tried to find out the point when the damage propagation in the data set starts. Meaning that when the actual damage to the turbofan happens. Okay, I have to. Okay, and as you can see here, we implemented this in Heuristic Lab as well. You can easily track exactly the point. When both of these bars, as you had seen in the middle of this videos, are somewhat in the middle and no so-called ensemble model is really winning, meaning that a stable state is detected, then we have a current concept shift or concept drift ongoing, meaning that this is the point where you should trigger maintenance. Well, we did this with a so-called sliding window application, sliding window evaluation, and the result was a tunable controller for state detection and concept drift detection. And coming to the end of my presentation, I'd like to summarize that of course, we had some promising results, but the most interesting thing is probably that we implemented the prototypical decision support system when to trigger the actual maintenance actions. Critical aspects for the success of these algorithms are always their tuning, the dataset quality, and the effort you have to spend in order to evaluate your data stream, which can be quite voluminous. Okay, last things. Predictive maintenance has big potential since it's connected with Industry 4.0, which is something everybody talks about right now. And it can, of course, be one step ahead, productivity and sustainability. Predictive maintenance, as I said just now, is also driven by the topic of connected vehicles, as we heard before in the former presentation. And our next steps will be to test these approaches on real-world data set, which is kind of hard to get because everybody's interested in this application. Nobody wants to hand out confidential data. And of course, we have to adapt our algorithms and implement some enhancement on them. And the very next thing we're going to do is actually to set up some prototypical system, as I've shown you in this presentation. Okay, thank you.